This video will go over sections 8.2 on electrolytes and non-electrolytes. So, a substance that can conduct an electrical current in water is called an electrolyte. And so here you have an illustration that shows an electrical circuit where the wires are going through water, or it's actually NaCl in water, so it's a salted water. And you have the cathode and anode dipped into the solution. And if you turn on the electricity, you see that the bulb will be lit, brightly lit. And so that means the liquid in the beaker here is able to conduct the electricity from the cathode to the anode, or vice versa, and that allows the electricity to go through. And so if you look at the atomic level, what happens is that the reason why electricity is conducted by a solution of sodium chloride is because when sodium chloride is placed into water, it completely dissociates into ions. Here it shows how NaCl as a solid, when placed in water, water is above the arrow to show that it's placed in water, dissociates into its ions, which are Na plus and Cl minus. And you see that the phase for Na plus and Cl minus are aqueous. And so when you have ions in solution, they can move, they can freely move, and that's why they will be able to conduct the electricity. And the positive ion will be attracted by the negative electrode, and that's the sodium, and the negative ions will be attracted by the positive electrode. And so because they are moving freely and going into the right electrode, they will conduct the electricity. So by opposition, a substance that does not conduct an electric current in water is a non-electrolyte. So the illustration here shows the same bulb with the same electrodes, but this time it's dipped into a solution of methanol. CH3OH is methanol. And methanol, when dissolved in water, because here it's an aqueous solution of methanol, it's not dissociating into ions, it stays as the molecule of methanol, CH3OH, which is neutral. It's a neutral formula. So there is no electrical charge, and so the electricity will not be conducted by a neutral molecule, because neutral molecules will not be attracted by the positive or negative charges of the electrodes. So typically covalent compounds that are neutral molecules will not conduct electricity, and we call them non-electrolytes. So we distinguish strong electrolytes from weak electrolytes. And a strong electrolyte dissociates completely in water to form ions. And so NaCl that we saw earlier is a strong electrolyte because it completely dissolves into its ions, and it's no more a solid, it's only ions now in water. So we say it completely dissociates into ions, and so these ions will be able to carry the electricity. A weak electrolyte dissociates only partially in water to form some ions, leaving mostly uncharged molecules. And you can see here that the electricity is only weakly conducted because the light bulb is not fully bright, right? It's lit, but weakly lit. And a typical example of a weak electrolyte is HF, the hydrofluoric acid. When you place it in water, if you look at the equation below, it becomes H plus and F minus ions, but you see also that the arrow is not an arrow going from left to right. It's a double arrow that shows that it goes both ways, to the right and also to the left. So it's what we call a reversible reaction. because it goes both ways. The molecule HF dissociates into H plus and F minus, but the ions also combine together to bring back the neutral molecule of HF. So it's a mixture of both, and you can see from the illustration of the atomic level that you have a lot of HF molecules. HF, the white and green ball together, bonded, and only a few ions, one H plus and one F minus. So typically when you have a weak electrolyte, it's because it's really weakly dissociating into ions, and you have a very small proportion of ions in comparison to the amount of the neutral molecule. So because there is very few ions, then there will not be enough to carry the electricity very strongly, and so they will only slightly conduct electricity. And so that's why we call them a weak electrolyte. So this table summarizes what are strong electrolytes versus weak electrolytes versus non-electrolytes. So for strong electrolytes, you need to have ions in solution, which are, charged particles that can carry the electricity. And so if you have a lot of ions, they will strongly conduct an electric current. And there are all kinds of examples of that. And typically it's salts that are soluble in water, like NaCl, KOH, HCl, KBr, are all dissociating completely in water to form aqueous solutions of ions that can carry the electricity strongly. Now, weak electrolytes are made of a lot of neutral molecules and a few ions. So the molecule dissociates only slightly into a few ions. So those few ions will weakly conduct the electrical current. And examples are, for example, ammonia, NH3, CH3CO2H, which is acetic acid, HF, we saw earlier. So they will mainly stay as neutral molecule in water, and only a few of these molecules will dissociate into ions. And then non-electrolytes are made of molecules, which are neutral molecules in solution. And so because they are not charged particles, there is no way you can conduct the electric current. And so these will not be electrolytes. And examples are CH3, CH2OH, which is ethanol, H2O2, hydrogen peroxide, are molecules that stay as neutral molecules in water, and they will not be able to carry the electricity. So let's go through this learning check and classify each of these solutions as strong electrolyte, weak electrolyte, or non-electrolytes. So you're given the name, so it's an aqueous solution of Na2SO4 to start with. So Na2SO4 is an ionic compound. It's a salt, it's a solid, and when you place it in water, it dissociates into two Na plus ions and one sulfate ions. So hopefully you recognize in the Na2SO4 formula that you have the polyatomic ion SO4 there. When it's free from the compound, it becomes the ion with two negative charges. And then we know that sodium, when it's an ion, it's Na plus. And here the subscript of 2 after Na means you have 2 Na per formula. So when it dissociates into 2 Na plus ions and 1 sulfate ion. And so this is a strong electrolyte because when you place Na2SO4 in solution, it completely dissociates into ions. So the reason why it's an electrolyte, it's because you have ions being formed, on the right side of the arrow, And the fact that it's strong, it's because it's having a straight arrow going to the right, and it's not reversible. It's only going to the right and completely dissociates into ions. So then these ions will be able to conduct the electric current. So that's a strong electrolyte. Second example, sucrose, which formula is C12H22O11, also a solid. When dissolved in water, the equation here shows that when you place sucrose, which is a solid, placed in water, the arrow shows that it becomes a solution of sucrose, an aqueous solution of sucrose, because now the phase has become AQ for aqueous. So sucrose is a big covalent molecule that stays as sucrose in water when it's dissolved. And it's a neutral molecule, right? So there's no way it can conduct electricity because there is no charges, no electrical charges. It's not an ion. So that will be classified as a non-electrolyte. Third example, the weak acid acetic HC2H3O2, which is a liquid, and when dissolved in water, makes an aqueous solution of. So you see how, so from this formula, maybe you can see that if you remove the first H of the formula of HC2H3O2, you have C2H3O2, which is the acetate ion. If you look at your list of polyatomic ion, you will recognize this ion, and it's the acetate ion with one negative charge. So you see it on the right side with the H removed and then with one negative charge. And so that's the acetate ion. And that H, when it leaves the acetic acid, becomes an H plus. So when acetic acid dissociates, it dissociates into ions. So that means we will be able to conduct electricity. However, you can look now at the arrows, and you have an arrow going to the right and an arrow going to the left, which means it's a reversible reaction or dissociation. And the ions tend to combine together and bring back the neutral acetic acid compound. So, and typically those arrows look like they have the same size, but usually it's a small arrow to the right and a large arrow to the left. You have fewer ions than you have neutral molecules. So it's very few ions in solution. And so that means it will be only able to carry electricity weakly, which then makes it a weak electrolyte. Electrolyte because it's made of ions when it's placed in water, but a weak electrolyte because the proportion of ions versus the neutral molecule is small. And you know that the key to recognize that is in the arrows, the fact that you have a double arrow. So let's go through another practice exercise here and predict the products for each strong electrolyte. So here you are told you have strong electrolytes. And the first one is CaCl2, a solid, when placed in water, and it dissociates, right? It's a strong electrolyte, which means it dissociates completely, right? That's what strong electrolyte should tell, is that it dissociates completely into its ions, because CaCl2 is a ionic compound. So you need to retrieve the ions that make up this ionic compound formula. So you want to find Ca. Ca is calcium in the periodic table. It's in group 2A. So it's a predictable ion. And calcium, when it makes an ion, because it's in group 2A, it will make the calcium 2 plus ion, right? So you can write that it will dissociate into the calcium 2 plus ion, and the phase for the calcium ion will be aqueous because once it's in water, it's an aqueous solution of calcium ions. And then we need to find the anion. And here Cl is chlorine. Chlorine is in group 7A. It's also a predictable ion that makes a -1 ion because you do 7A minus 8 and it's -1. So it's a -1 ion. So it's going to be Cl -1 with aqueous for the physical state. And here notice how there is 2 Cl minus. You need to be aware of that and remember to write that it's 2 chloride ions for 1 calcium. You know that because there is the subscript 2 in CaCl2 that tells you there is 2 Cl for 1 Ca. And so that 2, the subscript 2, now will be in front of each chloride ion to say you have 2 chloride ions. Right? And so you see that if you do the crisscross trick, you retrieve this formula. So to make sure you don't forget that the subscript 2 here will mean 2 chloride ions. So that's the solution for the first one. Now K3PO4 is a salt, again, a solid. When placed in water will be also completely dissociating because you have been told it's a strong electrolyte. And strong electrolyte means they completely dissociate into ions. So that means you need to retrieve the ions that make up this ionic formula of K3PO4. So undo the formula again by looking at what kind of ions K is making. K is in group 1A, it's an alkali metal, so group 1A means it's going to be K+. Notice how there is 3K, right? The subscript 3 after the K means you have 3K. So that means you will have to write the 3 in front of K+. And the physical state will be aqueous. The potassium ion now is in solution in water, so it's in an aqueous solution. It's floating around among the molecules of water. And so you have 3 K+ ions when it dissociates. And PO4, hopefully you recognize that it's a polyatomic ion. So you want to look at your list of polyatomic ion and see that PO4 is the phosphate ion. And it has 3 negative charges. You can see that in your list of polyatomic ions. And the physical state here will be aqueous again, because now it's in solution in water. And so you can check here that indeed the 3 negative charges from the phosphate will be cancelled by the 3 positive charges coming from the 3 potassium ions. And so you would retrieve this K3PO4 formula for the compound between potassium and phosphate. So these are the ions they dissociate into.